for coming to this year's CRESP Early Career Program Seminar Speaker Series. It is our honor today to welcome our speaker, Yu Tan. He is a postdoctoral research associate at the University of Wisconsin-Madison. He's also one of the ECP committee members. Thank you for kicking off this year's speaker series. So Yu is a postdoctoral research associate at the University of Wisconsin-Madison. He obtained his PhD in civil and environmental engineering from the University of Wisconsin-Madison and the Bachelor of Science degree in hydrology and water resources engineering from China University of Geoscience. His research mainly focuses on the fate and transfer of PFAS in waste contaminant facilities and the environment. Today's topic is effectiveness of composite liners in containing PFAS. So let's welcome you, and the stage is all yours. And anyone who has questions can save to the end or leave a comment in the chat. You please give the speech.
Thank you. Thank you for the introduction. Yeah, can you see my screen? I'm sharing.
Yes, we can see the screen.
Okay, yeah, feel free to stop me. Don't have to leave the question to the end. So I'm glad to be here. My name is Yu, as Fangfei introduced, and my topic today is the effectiveness of composite liner in containing PFAS. Get the slides moving. Okay, it works. So that's outline for today. And so last year, DOE kind of published this guides for investigate PFAS at DOE sites. Okay. So DOE want to understand the PFAS at DOE site. Those as shown in this graph, that they want to investigate PFAS in the airport or the firefighting training site, and also this one. Maybe I can use this laser. And also the wastewater treatment plant, and including the landfill. So at DOE site, they received radioactive waste and also hazardous waste and non-hazardous waste. They deposit on site. We call the mixed waste disposal facility. DOE also want to understand the PFAS in this site. So that's why we conduct this research. And before we move to next step, let's introduce a little bit about PFAS. So what are PFAS? PFAS are organic chemical that's synthetic by humans that because of their broad application. We always say PFAS are everywhere because PFAS has been intensively used in our consumer products for decades. We show the graph on the left show the broad application of PFAS. We just highlight a couple of examples here. The first one, the firefighting foams that contain PFAS. And also the protecting clothes that contain PFAS. They can use the PFAS to resist water, resist oil. And also at the DOE, they use the pipe to transport the cohesive fluid, such as high temperature fluid. They use this pipe and they coat PFAS on this pipe to make sure that it works properly. And recently, we found that PFAS has a health impact at very, very low concentration. EPA require that the PFAS concentration in drinking water standard should be lower than 4 to 10 nanogram per liter. This is really, really low concentration that we can imagine. You have one drop of PFAS to a whole Olympic swimming pool that can exist the drinking water standard. So we need to treat those. And what are PFAS? PFAS are a group of chemicals. We have thousands of them. They share some similarity. You can see all the PFAS have a chain, carbon chain, and also a function group. This carbon chain, we can see they have carbon and fluorine. For common organic compound that we have carbon and hydrogen, they replace the hydrogen with fluorine. So we have this carbon fluorine chain. This chain do not have the hydrogen, so it can resist water. And those function group can typically resist oil. This makes PFAS has extensive use. And also the carbon fluorine bond is one of the strongest bond in the world. So this makes this PFAS very stable at high temperature, so we can use PFAS to resist heat. Right? And then, so when we use those PFAS on those clothes or those pipe coating, then those material will end in landfill, right? We deposit them into landfill, and the clothes degrade. But PFAS is very persistent to degradation because as we mentioned, that the carbon fluorine bond is pretty strong, make PFAS very persistent to degradation. They release PFAS to the leachate. The leachate is just the water that flows through the waste and combine those contaminants and go to the bottom of the landfill. Or in DOE side, we call the mixed waste disposal facility. So right now we have little information in this regarding what's the PFAS concentration in the radioactive waste leachate, but we have some information for the municipal solid waste leachate. And we can see those different disposal facility has the similar PFAS source, right? They all receive the products containing PFAS. They probably have some close PFAS concentration. The graph show on the left, that's from the municipal solid waste landfill leachate. We can see the concentration, PFAS concentration in the leachate is much higher than the EPA required concentration. This plot in log scale. We can see it's 1,000 times higher than that, right? So in the mixed waste disposal facility, we receive those material containing PFAS. The concentration probably much higher than the EPA required concentration. And the if CRABS can do research to investigate the PFAS concentration in radioactive waste leachate, that would be much, much helpful. But right now, we know that it's probably much higher than concentration. And then the concentration in the environment is required to be much lower, right? It's only 4 nanogram per liter. Then we can see the chemical will tend to move from high concentration to low concentration. It means that PFAS tend to move from the waste containment facility to the environment or groundwater. The key question I want to answer is here, whether our disposal facility can contain PFAS, right? That's a key question I want to answer. So let's move forward. We know that we have the leachate or just water containing PFAS in the waste containing system, waste containing facility, and they tend to move to the environment. Before they move to the environment, we have some strategy, right? We have we call it composite liner at the bottom of the landfill to contain all the leachate in the system. This composite liner typically include a layer of geomembrane, just here. I can show, not quite sure whether you can see my camera here. Just this is a layer of plastic here. And we know that this is typically HDPE, high density polyethylene. HDPE is very good at hold water. When we put water at the top, water cannot flow through it, right? So at this point, the geomembrane serves as a primary barrier to containing leachate and also PFAS. However, when we put this plastic on the ground and we have machine work about them, right? It tends to generate defect or hole at the top. So this damage water can flow through those hole and go to the environment. In this case, we still need the clay liner. We can use a competitive clay liner or geosynthetic clay liner. It put on the bottom of the geomembrane, so we can slow down the flow of water and also the contaminant in the leachate, right? So we can use the competitive clay liner or geosynthetic clay liner. Competitive clay liner we can show in this graph. Just we find some clay source around the disposal facility. We just transport the clay here and compact in field to get high density and low permeability. Or we can use geosynthetic clay liner. Geosynthetic clay liner just this is a manufactured material that we contain a layer of high swelling clay we call bentonite by 2 geotester. We can lay them on the ground and then they can generate low hydroconductivity. So this works well. So we have the geomembrane plus clay. These two work together to contain contaminants in landfill. This has been demonstrated to be very effective to contain all different type of contaminant, but not PFAS, because this is not designed specific for PFAS. So we need to evaluate this. So that's the hypothesis that we propose how PFAS may transport through the composite liner, right? The first graph that we show on the left illustrate that when the geomembrane is intact, water cannot flow through it, but the organic chemical may still diffusion through it because we know that we have PFAS in the leachate at the top of geomembrane, and they are organic, and also geomembrane also organic. Organic chemical may tend to like organic chemical. They may accumulate on the surface of geomembrane and then diffusion through geomembrane driven by the concentration gradient between these two sides of geomembrane, and then partition back to the water, pour water in the clay liner, and then diffusion through the clay. And also, if we have a defect on geomembrane, means that water can flow through it with PFAS, then PFAS can advection through the clay liner, right? And in the field, we have these two parts on the clay liner because we have a couple of defects, but most of the part was protected by the intact geomembrane. So we identify a couple of key parameters that control the transport of PFAS through geomembrane, through the composite liner, right? So based on this, we develop this research. This means that we measure the key parameter that control the transport, and then we apply those parameters include the partitioning or adsorption of PFAS to geomembrane and diffusion of PFAS through geomembrane, and also hydroconductivity of the solution with PFAS to the clay liner. We generate those parameters, we measure those parameters in the lab, we generate those parameters, apply to a model that we develop that we can predict PFAS transport through composite liner. Then we can evaluate the effectiveness of composite liner in containing PFAS. So that's the first test we run. We call it, that's the batch test. Very simple. This means that we try to evaluate the PFAS partition from the aqueous to the geomembrane surface. We cut the geomembrane into pieces, and then we prepare some solution. We can use DI water or the municipal solid waste leachate, and we spike with PFAS to a known concentration. And then we mix them into the container, different container we use. And then we can track the concentration in the aqueous, right? We use different, at the geomembrane HDP, we also use HDP bottle, right? This kind of PFAS can partition to the surface of geomembrane, then they partition to the bottle, right? We have two things to address this concern. The first one, we can see the surface area of the bottle is much lower than the surface area of geomembrane in this whole system. So if the PFAS can partition or adsorption to the geomembrane, they may adsorption more to the geomembrane and less to the bottle because more surface area of geomembrane and less surface area of bottle. And we also run a control test. This control test means that we mix the same solution and the same bottle without geomembrane. Then we can address the potential partitioning or adsorption of PFAS to the bottle. So we shake those, mix the geomembrane and the solution in the bottle. We shake them and we track the concentration in the aqueous. Then we can do some mass balance to address the PFAS concentration on geomembrane, right? So that's we show the PFAS solution that we use. We use the single PFAS, meaning that we spike the PFAS into the solution with only one single PFAS, or we spike the multiple PFAS into one solution, and we mix with the geomembrane. For the solution that we use, the synthetic municipal solid waste leachate. This means that we dissolve some salt into DI water to mimic the chemistry of the municipal solid waste leachate in case that the NA strength may affect the partition. And we also use DI water, just pure DI water, and dissolve with the PFAS solution and target to this different concentration. With two geomembrane, the first one is these two are all commercial available. That first one has the smooth surface, and the second one has the texture surface. The surface there are a little bit different, so this may have some different adsorption. So that's the result. The graph on the left that shows that's the ideal result. We are looking for some result like this, that we will report the result as the relative concentration. This means that the concentration in the test bottom with geomembrane and compare to the concentration in the aqueous just without geomembrane. That's our control test. And we compare this at the same time. So we can plot this relative normalized concentration as a function of time. We look for some, if they have some adsorption, the concentration will decrease over time. Okay? And here is the real data. So we do a couple of tests. We do the single PFAS or multiple PFAS. We analyze, target 7 different PFAS with different function group and different channels. And we measure the concentration over time. That's the normalized concentration again. But we found most of the concentration fall into this bound, this plus 9% or minus 13%. This kind of the reproducibility of the quantitation PFAS. It means that we send the same PFAS solution into the instrument for analyze. They will get some variation. That's the variation for the PFAS quantitation. And most of the PFAS concentration in the aquifers is fall into this range. It means it doesn't matter whether you have geomembrane or not, the concentration remains steady. And we get some variation because the quantitation. So these results indicate that the partition of PFAS to geomembrane is insignificant, right? We run this test for about 50 days. Or we can see the absorption of PFAS to geomembrane surface is insignificant. And we estimate the partition coefficient of geomembrane is much lower than 1. We cannot get the exact value here because this is insignificant partition, but we can know that it's lower than 1. And then the next step, we try to mimic what happens in the field, right? In the field, we have leachate at the top and the less PFAS at the bottom. So we have a geomembrane here to separate two space. The first one that we spike with PFAS solution with known concentration, and the other side we spike with the same solution just without PFAS. And this is the image of the instrument that we use. And we track PFAS concentration in the source that initially spike with PFAS or PFAS-free solution. So we can know at specific time how many PFAS migrate through the source to the recipient. Right? Again, we measure we test the single PFAS, and that's the common PFAS in landfill, and also regulated PFAS, and also the mixed PFAS solution. And we spike them into MSW leachate or the DI water, and we test these two commercial available GCL and geomembrane, commercial available geomembrane. And we test one more geomembrane. This is a thin geomembrane. The company manufactures specific for this research, so we can short the transport distance from the top, from the source to the recipient. So hopefully we can generate some data in reasonable time. And we also run control test, means that we are not test geomembrane, we run aluminum plate, because we do not expect that PFAS can diffusion through aluminum plate in the testing time. So that's the control test. So here is the result that we test different geomembrane and different PFAS. We still test these 7 PFAS, and with different initial concentration. This time we report the result as the PFAS concentration at a specific time normalized by the initial concentration. And the graph is shown here. It doesn't matter what geomembrane you test, as long as it's HDPE. We can find the concentration can be lower or higher than the initial concentration. And most of them fall into this reproducibility area. This means that we test this geomembrane for about 1,000 days, and we didn't find significant PFAS loss in the source. This means 2 things. The first one, the PFAS are not partitioning too much on the surface of geomembrane. If PFAS can absorb by geomembrane, we lost some PFAS in the source, in the PFAS source, right? But we didn't find that. This confirmed with our previous result that the partition is relatively small, and also we didn't have too much PFAS diffusion through the source to the recipient. This means that we have very low PFAS diffusion from the HDPE geomembrane. And we can see it's comparable with aluminum plate, right? Those data as aluminum plate, we get some variation for aluminum plate too. At the same, we get the geomembrane, yes. Although we tested for 1,000 days. And then we look at data in the recipient, initially no PFAS. And then we get some sample. We get sample from those chamber, and we send into the instrument to analyze PFAS concentration. We do get some signal from those from the solution in the recipient, but most of the PFAS are lower than the limitation of quantitation. This means that PFAS concentration in the recipients are too low to measure. We get a couple of signal here. We can see this one that exceeds the the limitation quotation, but when we run it for 1,000 days, it disappears. This is probably biased, but again, this is just too low to measure. We don't know the real concentration in the recipient because we have a very small amount of PFAS that may transport from the source to the recipient through the gel membrane, just too small, even though we run it for 1,000 days. So, but we know for sure this concentration is lower than 40 nanogram per liter. So that's the conclusion that we have here. So it means that HDP gel membrane is highly effective to containing PFAS. And then, so we get those data, although it's not as we expected, we didn't get any trend here. We didn't find, the significant PFAS partitioning and PFAS diffusion through the gel membrane. But we still want to get some parameters so we can use in our modeling, right? So we just based on the recipient data here. We assume, we don't know the real concentration in the recipient, but we know that they are lower than 40 nanogram per liter. So we assume that it reached 40 nanogram per liter at the end of the test. So then we can estimate the parameter. This parameter is supposed to be the upper bound of the diffusion coefficient. So we do two things to estimate this parameter. First one, we do the relatively simple test or simple assumption that we use the first Fick's law. We assume the concentration in the source and recipient are constant. Then we can calculate this number. That's the diffusion coefficient. And we can also build a modeling that we will discuss this soon, that we use a modeling to simulate this transport process, and we can estimate the parameter. And we can see these two numbers are very close. So this kind of confirms that our modeling seems work for estimate the parameter. And we know that these are the upper bound of the diffusion coefficient. And we combine the diffusion coefficient with partition coefficient to get the permeation coefficient. So we know that this is the upper bound of the permeation coefficient. In reality, the permeation coefficient of gel membrane will be even lower than this number. And we pick this one for the following analyze. And we compare those permeation coefficient with the permeation coefficient of other organic compound in landfill leachate. We can find those such as toluene, this is about 10 to -11 square meter per second. And for PFAS, they are 10 to -15. This is orders of magnitude lower than toluene, right? This means that the gel membrane is more effective, much more effective to containing PFAS than containing toluene or the other organic contaminants in landfill leachate. So that's the short summary for this section, right? For gel membrane, we run this test nearly about 1,000 days, and we didn't find any significant partitioning, any significant diffusion, and this confirmed that the HDP gel membrane are highly effective in containing PFAS. And we generate this parameter for the modeling part. Then we shift to a different scenario. So previously we work on gel membrane because most of the gel membrane are intact. The water cannot flow through it. If they want to transport through the gel membrane, they need to diffusion. But we have some defect that the water on gel membrane, in this case, water can flow through it. So in these cases, the hydroconductivity or the permeability of the clay liner will be critical, right? And to slow down the flow of the water and also the flow of the leachate, of the PFAS. So we test 3 types of competitive clay and 3 types of geosynthetic clay liner. That's to represent different liners that we use in the field. We put them into this testing cell. We force water or leachate flow through the bottom and to the top. And we calculate or we record the flow rate, then we can know, whether this clay is permeable or not. And we test 2 types of solution. The first one that we put the same clay at the same condition with PFAS solution. And we also test the same clay, same solution without PFAS. The only difference is that whether with PFAS or without PFAS. So we can compare the hydroconductivity to see how PFAS may affect hydroconductivity of the clay. And we also track the PFAS concentration in the effluent and compare to the initial concentration we spec through the influent to determine whether the test can reach equilibrium. So we run different clay, different GCL, different solution. We run about 50, in total, we run about 50 tests in our lab. And that's the PFAS solution we use. We use the single PFAS, this 3, to represent, typical PFAS concentration in municipal solid waste leachate. And we create another leachate to dissolve or disseven PFAS to represent a field case that we have a landfill leachate from a field that we know this landfill have received intensive PFAS products. So those landfill leachate probably have the highest PFAS concentration in the field. So this is kind of extremely cases that we addressed using the field data. And again, we use 2 different solutions to host those leachate, those PFAS. We use the synthetic municipal solid waste leachate and also DI water. PFAS dissolved in these 2 types of leachate, and we run hydroconductivity test. We run 3 different types of clay and 2 different types of sodium bentonite GCl. Just as we mentioned, we have bentonite high swelling clay, and we run the test with the bentonite polymer composite geosynthetic liner. This means we mix polymer into the bentonite to enhance the performance of the geosynthetic liner. Then the next would be easier, that we run the test following the SDM standard, that we needed to at least reach the hydraulic equilibrium, means that we have the steady flow and steady hydraulic content and steady flow. And we also check the chemical equilibrium to make sure that they reach, there's no chemical reaction keep happening during the test. This chemical reaction may affect the hydraulic conductivity. So we monitor the effluent pH, monitor effluent electric conductivity, and also the PFAS concentration. If they are comparable with the influent, we can conclude that those, chemical reaction can reach equilibrium. So these are the example that we show to how we determine the hydraulic and the chemical equilibrium. For this one, that we plot all this graph as a function of time. This test has been run about 700 days. And we can see for this clay, this is GCl, FG, sodium bentonite GCl. It decreases and then remains steady and gradually increase and then remain steady for hydraulic conductivity on the left. And this CH clays remain steady hydraulic conductivity. So this means the hydraulic conductivity is steady. And we also have this Q out versus Q in. If Q out versus Q in is equal to 1, it means that you have the same volume of water come in, you have the same volume of water come out. This kind of indicates the steady flow. And for these 2 tests, we can see they all reach the hydraulic equilibrium, has the steady hydraulic conductivity and steady flow. And also for the EC and the pH, you can see those ones that plot compare the electric conductivity with the influent. We compare the outflow hydraulic conductivity to the inflow electric conductivity and also the pH. We can see that they are all fall into 1. It means that the electric conductivity in the effluent is comparable to the influent. This indicates, the reaction seems complete in the sample. And also we track the PFAS concentration in the effluent and compare the concentration in the influent for those tests with high PFAS concentration. And we can see for those clay tests, the GCL test, they nearly all fall into this close to 1 or within 20 times differences. But for the clay, they are not reach equilibrium, although we run about 140 days. So we need to run it longer to reach the chemical equilibrium. So this kind of summary of our test, we have about 50 tests have been run. The test has been run about 140 to 1,000 days, and all the tests meet the hydraulic equilibrium, but half of the tests meet the chemical equilibrium. And the graph on the right, on the left that we show as an example, we use the 1 GCl sample as an example to show how hydraulic conductivity change at PVF. PVF is just the volume of water influent as compared to the total volume in the soil sample. This you can use this as a time. It very has a linear relationship with time. So when we run the GCL sample with the we run two type of leachate. The first one just initial solid waste leachate. We run the same GCL with the same leachate. We run triplicate this open data, and we spike. We run different batch of tests. We just run the same GCL, same leachate. Only difference is we spike different PFAS into it, PFH, XA, PFOS, PFOA, and also those high PFAS concentration leachate. And we put this here. We can see the hydroconductivity decrease and then gradually increase and then steady for the control test. And that's the same case for PFAS. So it doesn't matter whether you have PFAS or not. The hydroconductivity are the same for the GCL. So this thing suggests that PFAS has negligible impact on hydroconductivity. And we can see the hydroconductivity kind of gradually increase. This is the impact of the inorganic part. So we found that inorganic part or inorganic salt dissolved in the solution can impact hydroconductivity, but PFAS seems to not have this impact, right? And then the graph on the right that we show all the data that we have, each data that compare to hydroconductivity. The x-axis that we run the clay or the GCL with PFAS-free solution, there's no PFAS. And the y-axis that we run the same clay and the same GCL, same solution, but only difference is that we with PFAS. We compare these two on this graph. So each point represents two tests. We have about 50 tests that are running in the lab, and this test has been run about. This is not weekly test. This run has about 1 or 2 years or up to 3 years, right? And we found there's no significant differences. There's no consistent higher or consistent lower hydroconductivity when due to the presence of PFAS. This kind of test suggests that PFAS has insignificant impact on hydroconductivity. And this 4 times bound indicates the reproducibility of the hydroconductivity test. This means that you run the same test with the same solution, run it twice, we get some variations. This is the 4 times. So that's the summary for this part that we run this test up to 1,000 days, and we found there's no adverse impact of PFAS on hydroconductivity. And then we put all those parameters we generate, we put them into a modeling. We list the parameter that we use here. That's our Galois equation for the transport and put them into a model. Then we can simulate the PFAS concentration in groundwater. And before we apply those models, we build some composite liner in our lab to generate data to validate the model. So that's the scenario that we simulate. That's the scenario we simulate. We simulate the geomembrane. We can use competitive clay liner or geosynthetic clay liner. We have an unsaturated subgrade that we change the diffusion coefficient with the degree of saturation. And we know that when we move out from the groundwater to the top, that the water content will decrease or degree of saturation will decrease. And we assume that the PFAS can only transport through the aquifers but not the air phase. So when the degree of saturation decrease, the diffusion coefficient decrease. So we apply this parameter. We divide it into 5 layers. We apply those parameters into each layers, and we can predict PFAS transport. And there are 2 things that we didn't consider. The first one, we didn't consider PFAS partitioning to the soil. And this is true for clay that we run some tests. We didn't find significant PFAS partitioning to the soil. And this may not true for the subgrade that contain high organic content. So PFAS may partition into the organic matters in the subgrade. And also the PFAS will partition into the air-water interface in the unsaturated part. So we ignore these 2 parts. But when we ignore this means that the prediction would be higher than realistic, right? So this means that we run a conservative prediction. So the modeling that we try to predict PFAS concentration at the groundwater table. So before we apply our model, we do some tests to validate our modeling, right? So that's the test we run. We have a geomembrane, we have a competitive clay liner, and below the geomembrane, we put some PFAS solution to mimic the landfill leachate that with high PFAS concentration. And we measure PFAS concentration in this solution and also the port A that in the pure water over time. And we plot the normalized concentration, means the concentration at different time over the initial concentration we put into the PFAS solution. We can see that in the soil that we didn't indicate or we didn't detect any PFAS in the soil, means that PFAS are not diffusion through the membrane to the soil. This is also confirmed with our previous test. And we didn't find any significant PFAS loss in the source. This also confirmed with our previous test. And we apply our modeling. We apply the parameter into our modeling to predict how long does it take to get, the measurable PFAS. You can see it's take about 10 years. The concentration will decrease about 5%, and we can get, a measurable PFAS concentration in the clay liner. So this means that our prediction fall into the range of our data, but the quantitation of PFAS, the barrier of quantitation is much higher than the data variation itself. So this is not necessarily confirm our model, right? So we should do something different. Then we use probably the data for toluene. That's we run the same test, exactly same test. Our lab ran this about 10 years ago. You can see it's about 2012. That we use the same geomembrane and the same, although we use the same clay. And we just use different compound, which is toluene. And we mentioned before that toluene has much higher diffusion coefficient through geomembrane, so it can easily to diffuse through the geomembrane. Right, and they share the same transport mechanism. So we put the data here. Those data points are reported by Park that our lab generated about 10 years ago, and those lines are our prediction. Now you can see the prediction kind of have a good agreement with our data. So this kind of validate our modeling. Then we apply our model to predict PFAS concentration at the groundwater based on this, this simplified the cross section of our liner. And we predict PFAS concentration at the groundwater as a function of time. We can see gradually increase and then reach the maximum. At 100 years for the competitive clay liner, the concentration is about 10 to minus 5 nanogram per liter. And for the GCL this is the CCL, this is the GCL, but they are all much lower than the EPA required standard for nanogram per liter. This means that if you have intact geomembrane, the composite liner are highly effective to contain PFAS. The PFAS concentration in groundwater are much, much lower than the required. However, if we also create a defect at this corner of the geomembrane, we use the symmetric boundary, and we observe the PFAS concentration directly below the defect as a function of time. We can see for the GCL, they are still much lower than the EPA required for nanogram per liter. But for the CCL, at this point, concentration exceeds the required drinking water standard. However, this is only the concentration at this point. We want to figure out what's the concentration distribution in this cross section, right? So that's the data we show, that we plot the PFAS concentration at this composite liner and also the subgrade above the groundwater. That's the groundwater. We simulate about 10-meter wide composite liner, and we use the blue color to indicate the low concentration and the red color to indicate high concentration. You can see below the defect, the PFAS concentration is red, means a little bit it's higher. However, when it's away from this defect, it dramatically decreases. And when it approaches to the groundwater table, it's all blue. Right? And we also monitor the PFAS concentration along the groundwater table, put here at 100 years. For the geosynthetic clay liner barrier, the concentration is, even though it's below the defect is low, and then dramatically decrease, and then level out to the concentration that is protected by the intact geomembrane. For the competitive clay liner, composite liner, the concentration below the defect is relatively higher than the MCL. However, it dramatically decreases when it's about 1 meter away. from this point. And then it decreases to the very low concentration that is protected by the intact gel membrane. So this result indicate that when we get a defect, the PFAS can elevate the concentration below the gel membrane. However, those elevated concentration is constrained in a very small area. The majority part of the groundwater is protected by intact gel membrane, and the concentration at groundwater is much lower. So how many defects we may have in landfill composite liner? We typically have 5 defects per hectare gel membrane. So we do some average calculation. So for the GCL composite liner, we have 5 defects per hectare. The PFAS flash is still much lower, only 0.003 nanogram per square meter per year. And for geosynthetic composite, it's even lower. Then just go to the end, the conclusion of the test. I separated them by 2 parts. That's experiment 1 that we found that the partitioning of PFAS to gel membrane is insignificant, and the negligible PFAS diffusion through gel membrane, although we test them for nearly 1,000 days. And the PFAS has no adverse impact on hydroconductivity of GCL and also CCL. And for the simulation, we found that PFAS concentration at the groundwater table is very low if we have a intact gel membrane. The impact of the defect on gel membrane is relatively limited, and the total fly through the composite liner is relatively low. And then that's the last that we, for the practical implication, we confirmed that the composite liner are highly effective in containing PFAS. And the GCL composite liner are more effective than CCL because the GCL typically has low hydroconductivity, so it's more effective to attenuate advection. Then they can decrease the PFAS concentration in groundwater table. And for practical engineering the barrier, that we need to limit the number of defects. Oh, and thank you. I'm glad to take questions.
Thank you, Yu.
Yeah.
Such a nice presentation. Anyone has any questions? Now is the time to ask them. Well, maybe I can start with one, I guess. Just curious, how did you prepare the spiking solutions?
Yes, so yeah, we have two group of solution that we prepared. First one, we purchased the concentrated PFAS solution from the market, and we dilute them into the MSW leachate or the DI water, so we can get the target concentration. But this one, that is when we purchase those, it dissolved in methanol to facilitate the solubility of PFAS into the solution. We concerned that the methanol may affect the absorption or hydroconductivity. So we also purchased some solid, pure PFAS, and we dissolve into water to prepare the concentrated PFAS solution, but that's methanol free. And then we dilute those concentrated PFAS solution into DI water or MSW leachate. Yes.
Did you verify the level of concentration you prepared?
Yeah, that's a good question. Yes, we did. But we found we assume this about, for example, we assume this is about 1,000 nanogram per liter. It varies. It can be 700 or 1,300. So that happens, because that's a huge dilution, because the concentration is just too low.
Yeah, that makes sense. And also the instrumental analysis uncertainty, that is about 30%.
So yeah, that
makes sense. But is there a big difference between using like a solution and you dilute it versus you use the solid to dissolve? Is the concentration very different?
I wouldn't say it's very different, but when we dilute the concentrated solution or we use a solid to dissolve, we weight everything that we use and we know the density, so we do some calculation. So this kind of get us close to the real concentration. And then when we prepare the solution, we send them to the instrument to analyze real concentration to confirm. I wouldn't say there are huge differences. The reason that we use the solid and also the liquid is the main reason because of methanol. Because we concerned that the methanol will, make
Yeah,
some differences in the test. Yes.
that makes sense. Thank you. Okay, let's go to other audience for questions. I think Nick raised the hand first. So Nick, any questions for you?
Oh, hi, Tan. Good
Hey, Nick.
presentation. So, I think I have two questions. One is
Yes.
like I see the slide 22, when you run the perm test, and it shows the breakthrough of the PFAS is slower for the the compacted clear liner, and you
Yes.
said GCL is faster. So do you have a reason for that? And maybe
Yeah.
how?
Yes. Because the GCL is thin is only 1 centimeter, and for the CCL is thick is about 5 centimeter. So it means that we have more pull in the CCL itself. So those data are CCL, and for those data are GCL. Meaning that you need more water to replace the poor water, then you can get the PFAS out. So this take a long time because the hydroconductivity of the CCL is still low.
And it's an advection driven transport, right?
Yes,
So
that's correct. Advection driven. Yes.
and this the CCL, how long you run the test here?
Yeah, for the CCL, both the CCL and GCL that we set up late about this year. So right now it's about 43 days.
Is that so if you run a model, for example, you have a model
Mm-hmm.
simulate your perm test, is that
Yes.
show
Yeah.
probably a same behavior or something?
Yeah, that's good. That's good point. We can simulate the hydroconductivity test in our modeling to estimate how long that we can get the effluent PFAS present in the effluent. I didn't run that, but we can see here that for the GCL at this low PVF, we still have some data that is below is not shown in the effluent. So this also confirm those. Right?
I see.
But we can run the modeling to adjust how long does it take to get the malleable PFAS in the effluent. That's good
okay.
suggestion. Yeah.
Yeah, that's good. And also for the so when you see the seems like the leakage is very localized and it's constrained to a small area. Do you also maybe just try and apply some interface gaps
Yes.
for
Yes.
different
Yes.
interface? I mean, it can definitely increase the influence zone, but maybe
Yes.
there's some limitation over there. So I just
Yes.
suggestion
Yeah.
on that. So yeah.
Yeah, that's true. That's true. We did a couple of one of these tests that we include one permeable layer between the geomembrane and also clay, so water can flow through those permeable layer and then flow down to groundwater. That's true. This can impact the influence area of the PFAS or of the defect. That's true. Yes.
Okay. Yeah. Thank you so much.
Thank you.
Nice presentation.
Okay, Stephen, please ask your question.
Okay, thank you. Hi, you. Thank you for your presentation.
Sure.
So I have two questions.
Yes.
The first is I noticed you work a lot with like nanograms per liter concentrations of material. How do you go about measuring something that's at that low of concentration?
Yeah, that's the real challenge right now. So you can see my data you can see the high variation. That's because they are too low to measure. But we use the HPLC, MS. So those instruments cannot develop specific to measure PFAS. That they has the capability to reach the limitation of detection down to nanogram per liter. So that's why we can measure those. But that's still challenging, I would say. Yes.
Okay, thank you. Yeah, I was just kind of curious what type of instruments you would use to do that.
We use HPLC MS. Yes.
Thank you. And also, my second question is going back kind of to the beginning of your presentation. You mentioned that there's all these different sources of PFAS to like the environment and stuff. Are are any of those, or how many of these are still active? Like, is there still a significant amount of
Mhm.
PFAS being generated today, or is that not as much of a concern today?
Yeah, that's a good question. So for PFAS, that we have thousands of PFAS, 5,000 or 5,000 or even more. So, but we the kind of well understand PFAS are mainly by two PFOS and PFOA. These are kind of more well understand, but for the others, we have little information about them. So right now, the US kind of phase out PFOS, PFOA. That's kind of the short chain or long chain PFAS. They have the longer tail of the carbon fluorine chain. This can be less mobile, so and can stay in the human beings for a long time. So this has more impact. So this has been phased out in the US, but I think that the industry still use the short chain PFAS. Those short chain PFAS can have replace the long chain PFAS, show the similar performance, but it can easier to be flow out through your body. So that's the use. So yeah, the long chain PFAS, PFOS, PFOA is phased out, but for the short chain we still use them.
Okay, so short chain is still being generated today.
Being used. That's what I learned so far.
Okay, thank you.
Mhm.
Any other questions from the audience? Okay, I'm gonna ask one more question.
Okay.
So when you did the simulation, I guess you did that for all of the PFAS you measured in the experiment. Did you see a big difference between, let's say, PFBA versus PFOA?
Yeah, that's what we was planning to do that, but unfortunately for the parameter we generate, that's the upper boundary for all the 7 PFAS that we got. So we only have the parameter for the upper bound. So we cannot tell the differences between the different compound, different PFAS compound, because we don't have the parameter. So we use this one to simulate all the 7 PFAS. They are different, but we don't have the parameter. So
Okay, thank you.
yeah, sure.
Any other questions from the audience? Okay. Thank you for the presentation. This is a good start for our this year's speaker series. We have more speakers in the future. Please stay tuned and hope everyone has a great holiday weekend ahead. Thank you so much. Bye.
Thank you.
Thank you so much.
Thanks. Thank you.